Dear students, good morning. Today, let us see the important problem on the design of the connecting rod. This is most commonly given question in end examinations. Okay, let us see the problem. Design a connecting rod for an IC engine running at 1800 RPM. They're given the speed 1800 RPM n value and developing a maximum pressure of 3.15 Newton per mm square. They are given the maximum pressure. Then diameter of the piston is 100 mm. They given the diameter of the piston is 100 mm. DOP. Diameter of the piston 100 mm, and this is the maximum pressure. And the mass of the reciprocating parts per cylinder is 2.25 kg. MR 2.25 kg, and length of the connecting rod is 380 mm. They're given the length of the connecting rod 380 mm. Here LOC, length of the connecting rod 380 mm. We are convert the same into meters, 0.38 meters, and stroke of the piston 190 mm. This is the stroke of the piston 190 mm. That is L, and compression ratio is 661. This is not required. Okay, and factor of safety 6. They're given the factor of safety 6. And take length to diameter ratio for big end bearing as 1.3 and small end bearing as 2. So here they're given the length to diameter ratio. Length to diameter ratio for big end bearing is 1.3. So here this is the small end and this is the big end. So at big end we have a crank pin, at small end we have a piston pin. Okay, that means they're given the length to diameter ratio for big end bearing means so this is belongs to crank pin. So LC by DC is 1.3. Then at small end the value is 2. That means LP by DP, length of piston pin to diameter of piston pin is 2. And the corresponding bearing pressures. The first we are talking about the crank pin, that is 10. This is 10. Next one is 15. That is about the piston pin. Where P is the pressure, B is the bearing. So bearing pressure for the piston pin. This is for the crank pin. Okay, this is for the crank pin. The density of material of the rod may be taken as 8000 kg per meter cube. They are given the density. This is the density. And allowable stress in the bolts as 60 Newton per mm square and cap as 80. This is the big end cap. Okay, the stress at big end cap as 80 Newton per mm square. And in the bolts, here we have to fix the bolts. Two bolts. This is one, this is one. So one and two. So here two bolts are there. So the allowable stress in the bolt is 60 Newton per mm square. Okay. Then the rod is to be of I section, made of I section. This is the I section, for which you can choose your own proportions. Use Rankine formula, for which the numerator constant may be taken as 320 Newton per mm square and denominator constant as 1 by 7500. So in this, they're given the numerator constant and denominator constant. So if you observe this formula, This is the crimping load formula. So in this formula, sigma CR is equal to FC by A is equal to sigma C by 1 plus K L by K whole square. So here we can written like FC is equal to A into, so sigma C into A by 1 plus K L by K whole square. So here if you observe here sigma C is in numerator and where K is in denominator. That's why we can call it as sigma C as numerator constant. C sigma C 320 megapascal. This is numerator constant and 1 by 7500 that is K. This is in denominator. So we can call it as a denominator constant. So here K is the in denominator. This is denominator constant. Okay. So this is about the given data. Based on the given data, you have to solve the problem. In this, they are asking about the design of the connecting rod. Design of the connecting rod. So you observe this figure, we are having different parts. One is small end, other one is big end, then big end cap, and two bolts are there, and this is the cross section. These are the major parts of the connecting rod. So if you observe this figure, yeah, this is the in detail figure of the cross section of the connecting rod. So this is the image available in the PSC data book 7.122 page. This is the thickness of the I section. This is the height 5T and this is width 4T. So in the first step, we have to find the dimensions of the I section of the connecting rod, like thickness T, height H, and B, width. So you have to find out these points from the design. The second one is the dimensions of the crank pin. See, are big end bearing and piston pin are small end bearing. So dimensions means here at the small end we have a piston pin. At the big hand we have a crank pin. So you have to find the piston pin and crank pin dimensions like length and diameter of piston pin. Similarly, length and diameter of the crank pin. So like that you have to find both dimensions. This is about the second point. Next one, size of the bolts for securing the big and cap. Yeah. So here, this is the bolt. You have to find the size of the bolts. That is the diameter of the bolt. You have to find that one. Next, fourth one. This is the big and cap. Here, the big and cap is the joined by the two bolts. Here, you have to find the thickness of the big and cap. That is the TC. The last one, you have to find you have to check the whipping stresses. Here, whipping stress is nothing but the bending stresses. As you know, due to the combustion, in the combustion chamber, in the piston, in the cylinder, the gas forces are acting from the piston due to the reciprocating motion. Okay, all the forces are acting on the connecting. Some of the forces are acting on the connecting rod. So, due to these forces, some bending action may taken place. So, to balance those forces, okay, to withstand those forces, yeah, whipping stress is there. So, we have to find the whipping stress, how much whipping stress is produces. So, the stress should be in a safe zone. That's why we have to find the whipping stress, how much it is releases. Okay, so this is the last point. So, our stress, it should withstand the stress. Okay, these points you have to find. Let us see one by one. The first one, dimensions of the I section of the connecting rod. This is the most important point. Sometimes they will given the same point for the 7 marks. in the examination. Only they will ask, find out the dimensions of the connecting rod. See, this is the cross section of the connecting rod. Here you have to find out the width, height, and thickness. So for that you have to use the clipping load formula. The same formula is available in the Mahadevan data book, 416 page, 19.3 page. Right. So in this formula, see sigma C and A. See in the data book, they already given. See, this is the PSC data book page. So this is a area 11 t square and moment of inertia and K. This all are given directly in the design data book, PSC data book. The same values we are taken here. So area 11 t square and K value, K square value 3.18 t square. There is some variation. So from that you can find out the K value 1.78 t. Okay. So the same values here you can use. Here you have to find out the t value. So we observe A is 11 t square and K is equal to 1.78 t. So here we have to substitute all the values in terms of the t. Okay. But to find out the t value, here we need Fc value, where Fc is the crimping load. Here we are having one more formula, Fc is equal to FL into factor of safety. So gas load into factor of safety. Here FL or FG, G per load, L per load. So G per gas, L per load. So you can use FL or FG. So load due to gas pressure. The same formula is available directly available in PSC data book 7.122 page. That is P into area. Same we have taken P into area. That is pi d square by 4 cross sectional area. Okay. So from this, D value, they're given the D value 100 mm diameter of the piston and P value maximum gas pressure 3.15. After substituting the factor of safety, they're given 6. So after then we got Fc value 148,440 newtons. Now we can equate the same two with the clipping load. So I am substituting here. Then Fc value, then sigma C value 320 megapascal and area 11 t square. Then 1 plus k, where k is the denominator constant 1 by 7500. Then L by k, where L is length of the connecting rod 380 mm and k small k, that is 1.78 t, 1.78 t. So here substitute the same value here, 1.78 t. Okay. So then after then here we can simplify easily. See, 148,440 by 320, 11 t square, 1 plus, after simplification you got 6.1, yeah, 1.78 t here whole square, so t square. This is a simplified form. So you can here, yeah, t square into 1, t square 6.1 by t square. So here t square will multiply with t square, we will get t power 4. So this is the final term. So this one is equal to this one. Okay, so from that formula, after simplification, this is a 464 into t square plus 6.1 is equal to 11 t power 4. Here further you can simplify more like t power 4 is equal like this. So you can divide with 11, then you will get t power 4 minus 40, so 42.2 t square minus 257. This is the final equation. Okay, if you observe, this will be looks like ax square plus bx plus c. Okay, but here square, but here t power 4. That's why let us take x is equal to x square. So after using the calculator, after using the calculator here in this format where a is equal to 1, b is equal to minus 42.6, minus 42.2, and c is minus 257.3. So from this equation we will get the x value or t square value. Okay. If it is in this format, you will get x value. But here the format is different. So you got directly t square, that is 47.6. I want only t value. So you will get root of 47, you will get 6.89, round figure 7 mm. This is the final thickness of the web bender flange. Okay, so like that, you can get the thickness value. Now, from this thickness, we can easily get the width and height. One is B, other one is height. 5 into T and 4 into T. One is 28, other one is 35 mm. So this is a very, very important point. This is for 7 marks they will give it. They will ask for 7 marks in the end examination. Okay, and the next one is dimensions of the crank pin are big and bearing and piston pin are small and bearing. See here, this is the piston pin connected to the piston. This is the crank pin connected to the crankshaft. Okay, yeah. So here they're given already LC by DC 1.3 and PBC. Similarly, they're given the one more LP by DP2 and PBP 15 Newton per mm square. So here also you have to use the gas load PL. So yeah, the load is acting on the piston pin bearing and crank pin bearings. As you know, if you observe, just wait. Yeah. So as you know, if we take the projected area, this is L and this is D. So here you can write like LP, DP or LC, DC. This is the projected area. So D into L. Here also D into L. This is for piston pin and this is for the crank pin. Next is the bearing pressure of the crank pin. This is bearing pin of the piston pin. So here pressure into area, projected area into pressure. Area into pressure, nothing but load, newtons. Okay. Here also Newton per meter, Newton per mm square and mm square, Newton and Newton. So like that we can balance the units. Okay. But here LC is from this equation, you can write LC is equal to 1.3 DC. You can write 1.3 DC. Here also LP is equal to 2 into DP. 2 into DP, here 1.3 DC. Here PBC values they're given 10 and here they're given PBB 15. This is the simplified term. 13D square, you have to equate this value with FL. This is 24740. Here also you have to equate the same value with 30 dp square with 24740 newtons. After simplification, we will get a direct DC value, round figure 44 mm. Similarly, from this term, you can find the LC value. Then you can round to 58 mm. Here also 29 and 58 mm. These are the dimensions of the crank pin and the piston pin values. Okay. Then third one, the size of the bolts for securing the big and cap. As I told earlier, size of the bolts. Here we are having the two bolts. We are having two bolts. Number of bolts are two. So here also you have to take the basic equation. 5 square by 4 into stress. Here NB is the number of bolts. Okay, 5 square by 4 into stress sigma T and NB. Here also this value will be equal to the inertia force. This value will be equal to inertia force. Okay, this is the direct equation available in the PSC data book 7.122 page. Here R is the weight and G is the gravitation constant. You know R by G. Here R by G is nothing but MR value. R by G is nothing but the MR value. So here you can substitute R by G with MR value. Then after that, so omega square R, here cos theta and cos 2 theta by L by R. So as you know, at top dead center on the exact stroke, theta value will be 0. 0. So initially, so cos 0 will be 1. Cos 0 will be 1. Then second one, cos 2 theta by L by R. L by R. Here also cos 2 theta or cos 2 0. Again the value will be 0. So the final value will be 1. Sorry, 1. This value also 1. So 1 by L by R. You can write R by L. You can write R by L. Okay. Yeah, L by R means 1 by L by R means R by L. So like that you can write. This is the final simplified. This is final simplified equation. Right. So from this, here MR value, they're given 2.25. They're given 2.25. And omega, as you know, 2 pi n by 60. They're given the n value 1800. Then R value, yeah, very important point here. They're given the L value. They're given the C. This is the N value and this is the MR value. They're given the stroke, that is 190 mm. So from that you have to take the crank radius. This is L by 2. So 190 by 2, 95 mm. You have to take the into meters. Okay. So like this, you have to find the R value. That is R is 0.095 meters. So 1 plus R by L. L of 0.938 meters. So this is the F5 value. So you have to equate this value with okay, you have to equate this value with inertia force. After simplification, you will get the DCV, that is the core diameter of the bolt. But if you want the nominal diameter, so for that you have to divide with 0.84, then you will get 11.94. The round figure value is 12 mm. So like that you have to find out the size of the bolt. That is the diameter of the bolt. Right. Next one is the fourth one, thickness of the. So next one, the fourth one, thickness of the big end cap. Sorry for the difference. So next one, thickness of the big end cap. See, here also you have to take the, this is the direct formula available in the Mahadevan data book. Cap thickness. This is the direct formula. TC is equal to, sorry, not this one, this one. See, this is the direct formula available in the Mahadevan data book. TC is equal to root of 6m by L3 sigma d. Okay. So here we need a L3 value and M value. So we have a direct formula for L3. This is the data book formula. This is the L3 value, L3 formula. Okay, see here also. This is the L3. L3. Okay. See here, distance from the center of the bolts is equal. L3 means distance from center to center of bolt. Okay. So bearing diameter. We are talking about the big end. At the big end, we have a crank pin. Okay, here dp means the diameter of the crank pin. Okay, here p means crank pin. Remember, dp1, diameter of the crank pin. That is, the value is 44. This is the 44. DC, the DC value is 44. Yes, you will see. Here also you can see. DC value is 44. The DC value, yeah, DC value is 44. 44. Same we have taken. Then 2 into, see here, 2 into thickness of bearing shell plus thickness of bearing value. The entire value will be, you can take it as a 3 mm. This value is 3 mm. Okay. 2 into 3. Similarly, bolt diameter plus allowance. The allowance is here 3 to 10 mm. So here again allowance also 3 mm. The allowance also 3 mm. And dB means diameter of the bolt. Diameter of the bolt. See, this is the diameter of the bolt. 12 mm. Okay, I have taken the same value. So 44 plus 6 plus 2 into 3, 6 plus, and diameter bolt 12 plus, again allowance 3, 65 mm. This is the L3 value. Okay, similarly, after getting L3 value, you need to find out the, after getting L3 value, you need to find out the M value. So this is the direct formula available in the Mahadevan data book. F5 L3 by 6. You got already L3 value. You need to find out the F5 value. So F5 also you know, that is 9490. You can refer the previous one, 9490. Yeah, this one, 9490. Yeah, FL, FLY. It's not FLY. F5, inertia force. This is 9490. So 9490 into L3 value by 6 value. Okay, we got the m value. Then you can substitute here. Here sigma d is the 80 Newton per mm square. Then we got the TC value. This is about the TC. This is we got around 11 mm. Okay. Now we have to check for the whipping stress. That is now we have to find out the whipping stress. Okay. Yeah, actually, these formulas are available in these formulas are available in Mahadevan DATABOOK. So by using these formulas, you can simplify the equation. See, here, as you know, V is equal to R omega. You can write V square by R as here. See, V square by R. V is equal to R omega square by R. So again, then R square omega square by R. So R square R. Then we'll get omega square and one R will be there. So simply, you can replace V square by R. You can replace V square by R with omega square R, remember. Okay. So in this equation also, this is Fi value and this is M value. So I have taken same value 2 into FIL by 9 root 3. So 2 into L 9 root 3. Here Fi is here. Okay. So 2L 9 root 3. Where as you know Fi is here W by T V square by GR. I have taken same value W by G. W by G and V square by 2 into R. Okay, in place of W by G, see, 2 into L, yeah, 2 to cancel, 2 to cancel. Okay, yeah, W by G is the M, V square by R. I have taken V square by R, and next one is L by 9 root 3. I have taken this value. Now, in place of V square by R, I have substituted the, see, R omega square. I have taken R omega square. Okay, so this is the final simplified equation. So that is the same equation I have taken here. This is the same equation I have taken here. See, m r omega square L by 9 root 3. M r omega square L by 9 root 3. This is the data book equation. This is the textbook equation. You can take any one formula. But before that, here M is the mass. See, here I have taken the M1 as mass of the connecting rod per meter length. Okay, so as you know, M1 is volume into density. Volume nothing but area into length. Okay, area into length. So area into L. Density is rho. So area is the 11 t square. You know, area 11 t square. 11 t square into L and rho. So 11 into t square. The t value. Silent. And L value that is 0.38 and rho value 8000. You got 1.64. You got 1.64. Okay. Now, but here I want only here m value. That's why I've replaced with m is equal to m1 into L. This is parameter length. Okay, so that's why I've replaced with m1 into L length. Okay. So after then, so m, in place of m, I'm written m1 into m1 into L. See, m1 into L. Here L is there, so L square. So m omega square R L square 9 root. This is the simplified formula. Okay. Now, in this M1 value 1.64, 1.64, then omega 25 n by 60 r square, n value 1800, and r value crank radius 0.095, and again L 0.38, 9 root 3. This is the maximum value. Okay. Now, I have to find out the sigma b, that is the bending stress or whipping stress. Okay. M by Z. I need Z value, section modulus. We have a basic formula as you know, Z is equal to I by Y. I by Y. Here Y is equal to B by 2 or H by 2. Here H is the 5T. Okay. 5T by 2. Okay. As you know, I value, as I told earlier, I value in shown in earlier. See, 419 T for 4 follow. See, you can see here. I value. You see, I value 419 by 12. 419 by 12 T for 4, right? I have taken same value here. See, 419 T for 12. If 5 by 2 by 2 by 5t. So after getting simplification, we'll get 13.97 t cube. So this is the final. As you know, t value is 7. So 4790 cube is z value. But I want sigma b value, m by z value. So m value is 51,300 and z value 4792. This is the 10.7 Newton per square. So since the maximum bending stress index is less than the allowable stress, in the question they're given the allowable stress, that is sigma d. In sigma d, they're given the allowable stress in the cap. See sigma d. See, this is the allowable stress in the bolts is 60 and cap, see 80. Okay, 60 and 80. So this value is less than the 80. Okay, so less than 80. So our design is safe. So like that, you have solved the problem. This is very, very important, commonly given in the end examinations. Okay, so design of piston, cylinder, and connecting rod. In either our questions, connecting rod will be given maximum, and next to piston or cylinder will be given. Okay, like that you have to prepare. Thank you.